Look closely at the human epidermis, and you'll find it isn't a static barrier. If you dive past the surface into the deep pores, it reveals itself as an active biological ecosystem, and often a battleground. Conditions like dandruff and seborrheic dermatitis are commonly misunderstood as simple fungal overgrowths. In reality, they are the result of a highly specific, hostile metabolic reaction occurring deep within the tissue. The etiology of these conditions relies on the Malassezia triad. At the base of the hair follicle sits the sebaceous gland, producing lipid-rich sebum. Malassezia fungi, a genus of lipophilic yeasts, naturally colonize this exact lipid-rich environment. The fungi survive by secreting enzymes called lipases. These lipases actively cleave the sebaceous triglycerides found in the sebum, breaking them apart and leaving behind distinct byproducts, primarily free fatty acids like oleic acid. These oleic acid molecules then infiltrate the upper layers of the stratum corneum. In susceptible individuals, this specific barrier breach triggers an aggressive immune response, resulting in the rapid cell turnover, flaking, and severe inflammation characteristic of dermatitis. Treating this condition requires stopping the triglyceride cleavage at the source. It is a localized lipid metabolism problem, requiring intervention at the exact site of the sebaceous gland. To suppress this biochemical cascade, dermatologists typically rely on a standardized topical protocol. This involves a dual-action strategy, applying an azole antifungal, like Sertaconazole, to halt the fungal synthesis, paired with a corticosteroid, such as beclomethasone, to suppress the host's local inflammatory response. In isolated laboratory conditions, this approach succeeds perfectly. Azoles demonstrate an exceptionally low minimum inhibitory concentration, or MIC, against Malassezia. MIC is the lowest concentration of an antimicrobial drug that prevents visible growth of a microorganism after overnight incubation. In a petri dish, the fungi are easily neutralized, yet in actual patients, standard topical creams often fail. The stratum corneum is a rigid brick-and-mortar structure designed to keep foreign substances out. When a standard cream is applied, only a negligible fraction of the active drug particles manages to slip through this dense upper layer. The pharmacological cure exists, but delivering it past the barrier requires advanced physical chemistry and nanoscale engineering. Clinical efficacy is completely dependent on the optimization of the delivery vehicle. A highly potent drug is effectively useless if it remains physically locked out of the combat zone. To bypass the skin's defense mechanisms, researchers replace standard creams with a mathematically optimized natural oil-based organogel. They utilized a 3x3 box Benkin experimental design to perfectly balance three critical rheological parameters. First is viscosity, second is spreadability, and finally, drug content. The box Benkin design is a statistical method used to create response surface models, minimizing the number of experimental runs needed to find an optimal formula. This is a 3D response surface plot, illustrating the interaction of these variables. By mapping the data, the model identifies a strict topographical target zone, pinpointing the optimal physical balance of 0.42 Pascal seconds for viscosity and 22.2 grams centimeters per second for spreadability. Variable A is cinnamon oil. It establishes the lipophilic base of the gel, while its active compound, cinnamaldehyde, acts as both a penetration enhancer and a secondary antifungal agent. Variable B is carbapol 934. Carbapol 934 is a high molecular weight polyacrylic acid polymer used as a thickening agent. It provides the required structural integrity for the gel, forming a cross-linked network that locks the active ingredients into place. Variable C is PEG 400. PEG 400, or polyethylene glycol 400, is a low molecular weight liquid polymer. It acts as a co-solvent and plasticizer, lowering the overall viscosity to ensure the rigid gel network can flex and spread evenly across the skin. By utilizing this mathematical modeling, formulators engineer a delivery vehicle that outsmarts the skin's defenses before a single batch of the drug is even manufactured. The box Benkin optimization yielded a precise, finalized formulation, designated as batch C11. C11 possesses a skin-compatible pH of 6.9. This neutral profile makes the gel chemically invisible to the skin's early warning irritation sensors, preventing an immediate rejection response. This is a particle size distribution graph generated via dynamic light scattering, or DLS. DLS is an analytical technique used to measure the size of particles in a suspension by observing how they scatter laser light. The data reveals a sharp, narrow peak, confirming the drug payload has been reduced to an ultra-small 231.3 nanometers. The formulation also recorded a zeta potential of negative 24.6 millivolts. Zeta potential is a measure of the electrical charge at the slipping plane of a nanoparticle in a liquid medium. This specific negative charge ensures electrostatic stability, creating a repulsive force that prevents the ultra-small particles from clumping back together. This nanoscale dispersion provides a distinct mechanical advantage. By reducing the individual particle size, the total surface area of the drug available for delivery increases exponentially. Rather than piling up on the surface, this precise nanoscale sizing allows the payload to slip through the previously impenetrable maze of the stratum corneum. The C11 organotol doesn't force its way through the skin. It uses precise nanosizing and electrostatic repulsion to bypass the barrier entirely undetected. To verify the physical structure translates to actual performance, the gel was subjected to in vitro Franz diffusion cell testing. A Franz diffusion cell is an apparatus that measures the rate at which an active compound permeates through a membrane, simulating human skin absorption. This chart tracks cumulative drug release over 8 hours. A standard cream aggressively plateaus early. Compare that to the optimized C11 batch. It draws a straight upward trajectory, achieving 98% delivery. This is zero-order release kinetics, a constant delivery rate, completely independent of remaining concentration. Zero-order kinetics prevent the rapid dump and subsequent plateau failure seen in standard creams. Instead, the optimized C11 gel precisely paces the delivery, continuously fighting the hostile fungal infection over the entire 8-hour period. Moving from artificial membranes to ex vivo permeation studies on living rat skin models confirms this kinetic superiority holds up in real tissue. When testing tissue retention rates, standard creams abandon the bulk of their payload on the surface, successfully driving only about 56% of the active drug into the actual skin layer. The C11 Organogel, by contrast, achieves a massive 86.14%. Rather, it requires engineering highly sophisticated physical chemistry that can systematically override the human body's own biological barriers.